Alright, Screencast, Unit 3A, Electron Configurations. Some of this will be a review from class, some will be new. Our objectives is to, again, cover electron configurations, including orbitals, remembering that those are probability models. You will need to know the shapes of the s and the p orbitals. We're going to apply Hund's rule, Aufbau's, and the Pauli exclusion principles, maybe without naming them explicitly, but we will definitely apply them. Write electron configurations for the element with atomic numbers 1 through 54. Be able to determine what element, given the electron configuration or the orbital notation. Be able to draw orbital notation for elements with atomic numbers 1 through 54. Define what it means to define valence electrons and inner core electrons, and then know what is meant by and be able to write and identify the noble gas electron configuration shortcut. Just to review, the nuclear model of the atom. The atom, as we know it today, has a small, dense, positively charged nucleus that is in the center. That nucleus contains protons and neutrons. The remainder of the atom and most of the volume of the atom is mostly empty space with electrons traveling. Electrons have a negative charge. And if we were just look at the picture, okay, the atom is neutral. If I'm talking about an atom, I have the same number of protons as I do electrons, same number of positive charges as negative charges, so it is neutral. Okay, that nuclear charge, remember the protons are in that nucleus, so it has a positive charge. That's balanced by the presence of those electrons, and they move about the nucleus. Okay. The question is, what are these electrons doing? How do they arrange themselves? How do they move? Okay. If we take a quick look and we were to look at an old model of the atom, that being the Bohr model, there were energy levels. Quantized just means that they were specific energy levels, and electrons have to be in an energy level. They can't be between energy levels. Those electrons in the Bohr model move in a circular. If I represent the nucleus as a plus charge, the Bohr model had these orbits. Okay, and these electrons traveled in these orbits. Okay, now electrons can actually move from one energy level to another. They do that by absorbing light, and I'm going to draw light as that because light does actually have a wavelength associated with it. Okay, if that electron is hit with enough energy, okay, it becomes excited and actually jumps up in energy level. Okay. Now, if you remember from class, the electron rules, electrons like to be at the lowest energy level. So what that electron does is it, in turn, shoots off a little photon of energy and it jumps back down to where it wants to be at the lower energy level. We'll talk about this in a different screencast as well, but I did want to introduce this concept of having discrete energy levels. Electrons have to be on an energy level, but they can move between them. Now when we talk about electron configuration, the electrons are all in the ground state or the lowest energy level. Okay, and again, Bohr's model was incorrect. Electrons do not move in a circular orbit. Okay, well, where do they move? Well, they move, or actually they're found in things called orbitals. These orbitals are really a space about the nucleus in 3D where the electron is probably going to be found. Okay? It gives no information about when the electron actually occupies a certain point in space, nor does it give us information about how it moves. How does it get from one spot to another? All it does is define a three-dimensional space where the electron is likely to be found. This has been backed up with experiments, so it is accepted as the model of the atom. Okay, so these orbitals, they really don't have sharp boundaries. They're kind of fuzzy because it is a probability model. Okay, and they kind of picked this 90% and said, okay, 90% of the time the electron is probably found within this volume about the nucleus. And that's what they defined as these orbitals. Okay. Hydrogen has energy levels, and we talked about this in class, main energy levels. They're also called principal energy levels, and we label them with whole numbers. And if you notice, okay, this N is the symbol representing a main energy level or a principal energy level. So N is a main energy level. Also called principal energy levels. Okay, we represent those with whole numbers. And even if an electron isn't in there, the energy level still exists. It's still an area about the nucleus where electrons might be found. Okay, each principal energy level is divided into sublevels. We label these with numbers and letters, okay, and they indicate the shape of the orbital. Within those sublevels, we have orbitals, just like what was covered in class. Okay, this is kind of, I like this diagram because it does show that this first main sublevel in the main energy level 1, this is the S. In the main energy level 2, there are two sublevels, this S and the P. And if we look over here to further detail, it shows that the P is made up of that PX, the PY, and the PZ. Okay? Going into the third main energy level, it has three sublevels, an S with one orbital called the S orbital, a P with three orbitals, PX, PY, PZ, and then the D with 5 sublevels that we call D1 through D5. Then the fourth main energy level, 4 sublevels, S, P, D, F. I don't know why I drew A5, it's F. S has 1 orbital, P has 3, D has 5, the F has 7. Okay. These should be familiar. The S sublevels, okay, are shaped, oops, hold on, I'll get there, sorry. Okay. The S sublevels, again, like spheres, okay, S sublevel, S orbital, shaped like spheres. The P orbital shaped like a double peanut, oriented along the different axes. And when you put them all together, they kind of look like everlasting gobstoppers, and we'll do that with balloons later on. Okay, so what I'd like to do is go through the diagram that we made the other day in class, but look at it a little differently. And what we're going to look at is we're going to look at the main energy level, also known as the principal. We're going to look at sublevels. Sublevels. And we're going to look at orbitals and then number of electrons, maximum. So in the first main energy level, I have an S sublevel. In that S sublevel, I have an S orbital in the shape of a sphere, and it has 2 electrons. In the second main energy level, or principal, I have an S, and I have a P. That S sublevel has an S orbital, shaped like a sphere, but that sphere is slightly bigger than that 1s orbital. The P has those 3 orbitals, px, py, pz. Each of these orbitals has 2 electrons maximum in it. This P has 6. The second main energy level has 8. Okay, first main energy level had 1 sublevel. Second main energy level had 2. The third main energy level has 3 sublevels. They are the S, the P, and the D. The S sublevel has 1 orbital called the S orbital. Again, slightly bigger than the 2s. The P has a px, a py, and a pz. And then the D, 3, 4, has the D1, D2, D3, D4, and D5. That S has a maximum of 2 electrons. Each of these p orbitals, actually any orbital, has 2 electrons in it. Okay. So for this p sublevel, there can be 6 electrons maximum. For that D, it could have 10. That means for the entire third main energy level, I can have a total of 18 electrons. This should be a 2, sorry. Okay. Now, for the fourth main energy level, I'm not going to draw it. The fourth main energy level is going to have 4 sublevels. We're going to add an F sublevel. If the S has 1 orbital, the P sublevel has 3 orbitals, and the D sublevel has 5, 1, 3, 5. The F sublevel is going to have 7 orbitals. Each of those orbitals can have 2 electrons maximum. So the fourth main energy level can have a total of 32 electrons in it. Okay, that's looking at those main energy levels, sublevels, and orbitals kind of from a different angle than what we looked at in class the other day.